Hello and good morning, good evening, good afternoon, whenever we are watching this or you are watching this. This is part two of N15 periodic trends. So again, check the warning out. Same one we saw last time. And a reminder, we really want to pay attention to the what, the how, and the why, and you're able to explain the what, the how, and the why. So, periodic trends number two, the continuation of N15. All right, the next trend is called electronegativity. So, electronegativity, what is it? A measure of the ability of an atom in a chemical compound to attract electrons from another atom in a chemical compound. So, ultimately, we're looking at a bond. The ability to attract electrons within a bond. Ultimately, how strongly can one atom pull on the electrons being shared in a bond? Another way of proposing it. The how. Well, electronegativity is going to increase going up a group in the periodic table, and electronegativity is going to increase going to the right on the periodic table. Now again, our mantra from last time, size of radius versus strength of nucleus. We should know the direction the atomic radius changes and what's happening to the nucleus at the same time will help us determine which element has a larger electronegativity than another one compared to it. So put the arrow in it. So ultimately we're going up and to the right of the periodic table is an increase. We don't care about noble gases. They're the lowest. Remember, they have 8 valence electrons. 8 is the most valence electrons you can have. They don't want to lose any. They don't want to gain any. They don't care. Just leave them alone. So, little idea of electronegativity. It's an attraction. See? They're falling for him. He's so strong. Love. The greatest attraction of all. I don't know, just copying the slide. All right, so why? What's going on with electronegativity? Well, when you go down a group, we know the radius is larger. Therefore, electrons are in higher energy levels, and they're further from the nucleus. Which also leads us to increased shielding from those core electrons. There's less of a pull from the nucleus to the valence electrons. So the nucleus doesn't pull as hard on the bonding electrons from another atom. It's further away. Imagine two atoms bonded together, the nucleus of one atom trying to attract the electrons of the other atom, and vice versa, is much more difficult when the atom itself is very large due to extra energy levels. That's going down a group. Now, if we go to the right, we already said this, it's going to increase to the right. Well, we know the radius gets smaller. We know Z effective becomes larger. So, smaller radius, larger nucleus. That's going to make it for a very large attraction to a bonding atom's electrons. They can get really close to that nucleus. Greater attraction. Therefore, it has to have a larger electronegativity. Again, the nucleus is pulling harder on the valence electrons, which is where the bonding is actually occurring. All bonds, when we get to the bonding chapter, take part in or are used by valence electrons. Closer you are to the nucleus, stronger the attraction. Further from the nucleus, weaker the attraction, which is the same as the electronegativity. Any questions on electronegativity? All right. The next trend is reactivity. Some elements just react more than others. And part of it sometimes is just the nature of the reactant. It's the nature of the element that it is more reactive. And that's just the way it is with different elements on the periodic table. So basically what's going on is it's interesting here. Some elements, or sorry, all elements in a group tend to behave the same with their reactivity. Well, there's the same Z effective, and there is the same number of valence electrons. But the magnitude of their reaction is going to change. For example, on the how, on the left-hand side is column 1, the alkali metals. They become very reactive or an increase in reactivity as you go down a group. So sodium, it's lithium to sodium to calcium. No, not calcium. That's in the second one. I'm drawing a blank. Potassium. I already said that. Sorry. But anyway, column 1 going down, the radius gets that much larger. It's that much easier to remove that electron in a reaction. Very, very explosive. Conversely, go to the halogens. Column number 7, group 7 with fluorine. They increase in their reactivity going up a group. Well, as you go up the group, the radius gets smaller, which means the nucleus is closer to whatever that atom is bonding to. It has a stronger electronegativity. It can rip electrons away from other atoms completely, or even in a shared bond, attract them more. It's more reactive. Fluorine is more reactive than chlorine, which is more than bromine, which is more than iodine. So opposite sides of the periodic table, opposite reactivities, as they both increase, but column 1 increases going down, column 7 increases going up. We don't care about the noble gases because they don't react. Metals and nonmetals, again, opposite trends. Column 1 is alkali metals. Column 7 is the halogens. Noble gases are inert or non-reactive. They don't really do much. They don't want to gain electrons. They don't want to lose electrons. I know I'm being redundant with that, but that's just the way they are. So the why, kind of already alluded to it a little bit there. Metals increase reactivity going down, larger radius, increased shielding, lower ionization energy, easier to remove electrons. So again, size of radius versus strength of nucleus. The nonmetals increase going up, as we said. Smaller radius, greater Z effective, higher electronegativity, higher affinity, don't worry about that. So it's easier to attract electrons. Steal the electron, strongly share it, but not really. So again, opposite trends, opposite direction of trend for opposite reasons. All right, so in summary of all these trends we've seen over 2 days, ultimately comes like this. I'll let you take a look at it for a second. Notice the radius is the opposite of all the trends. So the mantra, size of radius versus strength of nucleus, plays a very important role with all the trends in your comparison of one element to another element or ranking things in a group of elements. This next slide is actually one of the glue-ins. I think it's in your reference sheet. It's also posted on this week's printouts for the week on the One Stop Shop. So check that out. This would be a good one to probably print out, shrink it down 50% or so it can be pasted nice and easy into your notes and go with it. But very supportive slide in your studying. All right, a couple videos that you guys can check out on your own. They're kind of fun to watch. So please check them out at your leisure, but they are interesting and exciting to watch, I think. Another video, kind of a quick summary, has explanation of some of the exceptions to the trend. We're not going to be focusing too much on those exceptions, so don't really need to worry about that. But it's still something I would suggest watching, just to kind of see and get an idea about it. Might be helpful, maybe clarify a few things as to why. If you have any questions on those exceptions, by all means, please come talk. Let's see what's going on. And then I'll give a YouTube link to this presentation. Clearly, you're already watching it, so you already have the link. But I thought I'd be redundant, because redundancies are amazing. So why not? All right, I'm going to stop the video here, but there are slides on electron affinity that are part of the presentation on the PDF on my website. You're not required to know this trend, so don't worry about it. But if you're interested in seeing what's going on, by all means, check it out. Thank you much, and we will stop here.